So today's lesson is about something called implicit differentiation. And I want to sort of point out to us, at this point, we're pretty good at taking derivatives of functions. But so far, we've really only ever taken derivatives of functions that are expressed like this, as y equals some function of x. But sometimes, particularly in sort of like more complicated, like real life situations, we're going to encounter functions and equations that are much more like this. Where it's not just y equals, but it's some other relationship between the variables. And we might want to know about dy dx. In today's lesson, we're going to learn how to find derivatives of relations like that without having to go back and like rewrite them in terms of in terms of x, like y equals f of x. Before we do that, let's go and take a deep breath. And let's begin. So before I go any further in this lesson, I do want to take a moment to talk about vocabulary, right? There's these two words that are going to be fairly important for this lesson, and they're the words explicit and implicit. And maybe I'm worried. I'm worried that some people think that explicit language means like bad words, like you see like content warnings on like music albums where it's like, oh, parental advisory, explicit lyrics. That doesn't mean that they're bad. It just means that they're very, very clear. There's no room for ambiguity. And so mathematically, when a function is expressed explicitly, it means that there's a very, very, very clear relationship between the variables in the equation. And we're going to look at examples of that in just a minute. Whereas when something is expressed implicitly, or when something is implied, it means that it's not expressed directly. The conclusion is something that the listener sort of has to pull from context. You kind of like, oh, are you implying that you did such? It means the person didn't say it, but you're getting kind of the sense from them about that, right? Sometimes in math we have explicitly defined functions, and sometimes we have implicitly defined functions. And again, it's not that one of them is bad and one of them is good, it's just that there are different ways that these things can be constructed. In these three examples over here, these are all explicitly defined functions. They are functions where y is defined explicitly in terms of x. When someone plugs in x, it's really clear how to get y. You multiply it by 4 and then you subtract 15. When someone gives you an x value here, I guess this one's more complicated, but it's still not unclear. You plug in the x values here, do this stuff, and y comes out at the end. This last one, it's got a tangent and a natural log. It might not be clear, it might be complicated, but there's no ambiguity here, right? You're going to take your x value and you're going to plug it in here, you're going to plug it in here, you're going to do a tangent, you're going to multiply by 2, subtract 4, do a natural log, add them together, blah, blah, blah. In the end, you're going to get y. There's no ambiguity here, okay? For these examples over here that are implicitly defined functions, when I plug in an x value, it's not a direct relationship to what's going to happen to y. I'm going to have to do something to x and add 4, and then I'm going to have to square root in order to figure out what y is. Do you see how in all of these ones, there's clearly a relationship between x and y, but it's not nearly as explicitly defined as these ones are? Everything we've been doing with calculus so far in this class has been on functions like this, explicitly defined functions. Today we are learning about implicit differentiation, and so you're going to use that for implicitly defined functions. Okay? So everything we've done so far has been on explicitly defined functions, but we want to make sure that we can do calculus on implicitly defined functions as well. That's what today's lesson is all about. So now that we've sort of got a sense for what we already know how to do and what we are going to learn how to do today, we can start moving into that. So I've got just a little bit more setup here, and then we're really going to be getting into some of the math, quote unquote, what you guys would think of as math, sort of the equations. So the first key point that I want to point out to us is that this year, all of the calculus that we're going to be doing is calculus of a single variable. There is something called multivariable calculus. You'll learn it at some point in the future if you choose to. What we're doing in this class is only single variable calculus. And if anybody's groaning like, oh, when do we get to the good stuff? There's a whole lot to learn about single variable calculus before you're really ready to do stuff meaningfully with multivariable calculus. But what this means for our purposes is that every equation will only have one independent variable. It's usually the x variable. Sometimes it's a t variable. Every once in a while it'll be something else. But generally speaking, it's those ones. those variables are often referred to as the variable of differentiation. The way that you can tell that, by the way, like when somebody says, hey, what's dy dx? The variable on the bottom down there, that's the variable of differentiation. So if at some point somebody asks you guys to find, hey, what is dv dt? That variable down there is the variable of differentiation. Just to be perfectly clear, if someone asked me to find dA dy, okay, great. Y is the variable of differentiation. You can always tell what the variable of differentiation is because it's the variable that we put on the bottom of our sort of like dy dx, dv dt notation. Okay, so we've got this idea of a variable of differentiation. Okay, now, next key point. Anytime that you are taking a derivative, you must know what the independent variable is. You must know what the variable of differentiation is. Again, it's usually going to be x, it's usually going to be t, but you got to know what it is before you take the derivative. And this next thing right here, this is the whole lesson. Right? This is the whole lesson summed up in one sentence. And we're going to do practice with it. We're going to talk about why. The whole lesson is summed up in this. Any time that you take the derivative of a variable other than that one, other than the variable of differentiation, you have to use the chain rule. Okay? And what exactly that means is something that I'm going to be making clearer as we go through these examples. But this is the entire lesson right here, summed up in one sentence. Anytime you take a derivative of a variable other than the variable of differentiation, you're going to have to use the chain rule. And it's going to be a really simple chain rule, but it's still a chain rule. Okay, so let's get into some examples that will help us to see this. Right? So suppose that somebody gave me the equation x squared plus y squared equals 4 and asked me to find dy dx. Okay, so if I wanted to find dy dx, something that I could do here, I could use a plot process called implicit differentiation. And when I do implicit differentiation, what I do is I take the derivative of both sides of the equation. So I have this equation, I have this relationship between x and y. The derivative of the right-hand side is really easy. The derivative of 4 is 0. Now let's look at the left-hand side. The derivative of x squared, what's the derivative of x squared? It's easy, right? The derivative of x squared with respect to x is just 2x. Now, the derivative of y squared. Well, the derivative of y squared, that's something squared, so it'll be 2 times that something times the chain rule. Remember I said up here, anytime you take the derivative of a variable other than the variable of differentiation, you got to use the chain rule. So I'm going to do 2 times y, whatever y is, times the derivative of what was inside. Well, what was inside is y. What's the derivative of y? What is the derivative of y with respect to x? We literally have a notation for that. The derivative of y is just dy dx. I don't know what it is, but I've got a name for it. It's dy dx. So what I did here is I took the derivative of x squared, which gave me 2x, and now I'm doing the derivative of y squared, which is 2y, times the derivative of whatever was inside. That's dy dx. Okay? So now, the problem said find dy dx, so I need to solve for dy dx. I'm going to subtract the 2x over. 2y dy dx is negative 2x. Then we can divide the 2y over. dy dx is negative 2x over 2y. So I guess the 2's would cancel. And we'd find that dy dx is negative x over y. And there it is. We found it. Okay. Now, some of you may be wondering, and I've taught this lesson enough times to know a lot of people ask this question, you may be wondering, why does the y squared term need a dy dx, but the x squared term doesn't? Okay? And I've got a way to explain that to you. I've got a way that I've explained it before, and it tends to help it make sense to people. So let's see. All right, so I kind of want to go through this guided example. This is like a 9-part example. And I just want us to think about what the derivative is, the derivative with respect to x of each of the following things. Okay? So what is the derivative of x squared? Right, well, I mean, you guys are really good at it. I mean, this is like the easiest derivative I could ask you these days, right? This is 2x. Okay? What is the derivative of the natural log of x squared? Well, this is a chain rule. There's something that's plugged into the x squared function. So I would do it's almost like we'd take a minute to say, the outer function is x squared and the inner function is natural log x. I think a lot of you guys actually skip this at this point, but some of you still write it, and that's fine. The derivative of the outer function is 2x, but we leave the inside alone. So it's 2 natural log x, and then times the derivative of what was inside, that's 1 over x. So I guess we could make this 2 natural log x over x. Okay, I'd like you to sort of pause the video here and go ahead and do these next 4 examples. And let's just sort of check and make sure that you can do the chain rule well. And then I'll connect it to why we need to do this dy dx thing. Okay, so the next one here, right? The outer function is x squared. The inner function is sine x. So this is going to be 2 times leave the inside function alone, sine x, times the derivative of what was inside. That's cosine x. Okay, great. This next one would be 2, leave the inside alone, cosine x, times the derivative of what was inside. Well, that's negative sine x. Yay, we're doing it. Right? The derivative of tangent x squared, that would be 2 times leave the inside alone, tangent x, times the derivative of what was inside. Well, the derivative of tangent x is secant squared x. You see how all of these things are just using the chain rule? What's funny is, if I wanted to, I could even do the chain rule on this one. I could say it's 2 times leave the inside alone times what's the derivative of the inside. And if I wanted to be really obnoxious, I could be like, well, it's dx dx. And it's like, oh, okay, fine, it's dx. Dude, dx dx is 1, which means this thing just turns into 2x. So you can even make the argument, sure, even with x squared there's a chain rule happening, but it's a useless chain rule. I don't have to do the chain rule. It gives me the same thing back. So now that we have this sense that we're doing this chain rule, let's look at what it would look like in these 4 problems that have y in them. If somebody wanted me to do the derivative of y squared with respect to the variable x, I would do 2y times the derivative of what was inside, dy dx. If I wanted to do the derivative of this thing with respect to x, well, it would be 2 times whatever was inside times, and now it's, well, times the derivative of the thing that was inside. Well, the derivative of the thing, derivative of 2y, well, that's 2 is a constant, so this would be 2 dy dx, and then, I mean, the derivative of 3 is 0. So, I mean, this is all sort of complicated, but this winds up turning into 4 times 2y plus 3 dy dx. Anytime I'm taking the derivative of something that has a y, a non-x, a non-variable of differentiation in it, I've got to use this implicit differentiation. I've got to use this sort of like chain rule process to remember it. Okay. If you're feeling up to it, go ahead and pause the video and take a minute to do this last one, just so you can sort of try it on a fairly simple example. So this one should be 2 times leave the inside alone, sine y, times the derivative of what was inside. Well, what's interesting is the thing that was inside actually also requires its own chain rule. The derivative of the sine of something is cosine of leave that thing alone, and then multiply by the derivative of what was inside. That's dy dx. So this last one, if I wanted to simplify it, would be 2 sine y cosine y dy dx. This is effectively an extension of us thinking about the chain rule, and we're going to use that for this process called implicit differentiation. So let's go ahead and go into a fairly simple example of implicit differentiation. I suppose it's not super simple, but it's where we're going to start. Okay, so I'm asking you to find an expression for dy dx. That means they want you to take the derivative with respect to x. That means x is our variable of differentiation. And so to find this thing, to take the derivative, we're going to use implicit differentiation. And that means that what I'm going to do is I'm just going to take the derivative of both sides. Okay. So on the left-hand side, I have a product rule here. There's a y squared times an e to the x. So let's start with the derivative of the first thing. What's the derivative of y squared with respect to x? Well, that's y, not x, so I got to do this chain rule. This is going to be 2y dy dx times, I'm doing the product rule, leave the e to the x alone, plus, now I'm going to leave the y squared alone and do the derivative of the e to the x. Well, the derivative of e to the x is just e to the x. And then equals, now I need to do the derivative of this side. What's the derivative of 5y going to be? Well, the constant multiple rule means we could sort of ignore the 5. 5 times the derivative of y is dy dx. All I did here is I went through and I did the derivative of each thing piece by piece, and I wrote the pieces out, and anytime I took the derivative of something that wasn't x, so this y squared here and this y here, I had to use the chain rule and I had to write in this dy dx. Now the last thing I need to do, the problem said find an expression for dy dx, and so I need to solve for dy dx. So let's see here. If I'm going to solve for dy dx, I want to move the non-dy dx things to one side and the dy dx things to the other side. So here on the left, I'm going to have 2y dy dx e to the x minus 5 dy dx equals negative y squared e to the x. Cool, yay. So now I'll factor out dy dx. Remember, I want to get dy dx alone. When I factor out dy dx, I've got 2y e to the x minus 5 equals this stuff. And then finally, I can divide this over. I get dy dx is negative y squared e to the x over 2y e to the x minus 5. And there it is. That's my derivative. And you might be like, what the heck is this? And I want to remind you, this is still a derivative. This is everything we already know about the derivative still applies. Remember that one of our main uses for the derivative has been to find the slope of a tangent line or to find the rate of change of the function. It's the same thing. You might be like, whoa, but this is like weird. I agree. So's this. Look, I have no clue what this thing looks like. Like, this is some weird exponential parabolic sideways something weird relation. It makes sense that its derivative is going to be all kinds of weird. But if you wanted to know what a slope of a tangent to this thing was, if you could plug in x and y, you could find what the slope of that tangent was. This is what we've done here. This is what we've found. Now, I kind of want to emphasize here that questions that we've done before, like how do we find the equation of a tangent line, those still apply. Right? If I gave you some weird function like this is like this thing's like an ellipse of some form. All right, cool. If somebody wanted to find the equation of a tangent line to this thing, all I would need is a point and a slope. Well, look at that. They gave me a point. All I have to do is find the slope. Okay. So what we're going to need to do in this problem is we're going to need to find dy dx. Then we'll plug in our point 3, negative 1, and that'll get us a slope, and then we'll write the equation of the line. Okay. I would encourage you all to pause the video and try and take this derivative on your own, and then go through these other steps. If you'd like, unpause, check and make sure you got the right derivative, and then move forward with it. Give yourself a chance to try and do this. So let's find the derivative. I'm going to do the derivative of both sides. So first, the derivative of 3x squared. Do I need a chain rule here? Nope, because I want to find dy dx. The variable of differentiation is x. So great, that's just 6x. Easy. Now we keep going, right? Now I've got negative 2x, y. Okay, so in this one I'm going to need to do a product rule. So the derivative of the first thing, that negative 2x, is just negative 2, and then I leave the second thing alone. The y just stays there. I don't need a chain rule because I'm not doing the derivative of the y part right now. But now product rule comes back in. Now I'm supposed to leave the first thing alone, and the derivative of the second thing, the derivative of y, that's dy dx. Okay? Then finally, I get to this last term, the derivative of y squared. Well, that's not an x thing, so I need a chain rule. The derivative of this will be 2y times chain rule, dy dx, and then equals, and then I need to do the derivative of the right side. Well, the derivative of 34 is 0. Okay, so I was supposed to find dy dx. Dy dx has appeared, now I need to find it. Now I need to get this thing alone. So I want to move these non-dy dx things over, okay? And I'm going to switch the order of these two things just because I like the idea of having the positive thing first. So I have 2y dy dx minus 2x dy dx equals, and then I would have moved the 6x over and the 2y over. Okay, now I want to find dy dx, so dy dx, I factor that out. 2y minus 2x equals this thing. And then I could just divide that thing over. So dy dx is going to be negative 6x plus 2y divided by 2y minus 2x. I could simplify that more if I wanted to, but this question isn't even asking for us to find dy dx. This is just like a step along the way. I really needed to find the slope. So to find my slope, I want to find the slope at the point 3, negative 1. So when I plug those points in, I get that dy dx is, well, let's see here, negative 6 times 3, that's negative 18. 2 times negative 1, that's minus 2. Over 2 times y, so that's negative 2. And then minus 2 times 3, that's 6. So this is negative 20 over negative 8. Let's see, those are both divisible by 4, so I could reduce this down to 5 over 2. Great. I now have a slope, and I have a point, which means I can write my tangent line. It's going to be y minus negative 1 equals slope times x minus 3. And we're done. If I were to graph this ellipse and graph this line, we would find that they're tangent at 3, negative 1. So everything we've learned before about the derivative and what we do with it is all still totally valid. After this example, I'm going to get to one more example of how we can use this process of implicit differentiation to do some of the same calculus we had before, but I did want to just put in one more, sort of just purely find an expression for dy dx. One more example, just to make sure you guys get one more opportunity to sort of practice this thing and make sure you're feeling okay about it. So let's find an expression for dy dx if this is the relationship between x and y. So again, I'd recommend that you pause the video, give this one a shot, and then we'll check it together. All right, so we're going to use implicit differentiation. I'm going to do the derivative of both sides. First, the derivative of the left side. That e to the x, it's in terms of x, so I don't need to worry about a chain rule. The derivative of e to the x is just e to the x. Plus, now this next thing is a product rule. There's an x and a sine y. The derivative of the x is just a 1, and I leave the sine y alone. Plus, now I leave the x alone, times the derivative of sine y. Well, I'm having to do the derivative of something here that's not just x, so I need to be on the lookout for a chain rule. The derivative of sine y is cosine of leave the inside alone times the derivative of what was inside. Well, the derivative of y is dy dx. Okay. Now equals, I also need to do the derivative of the right-hand side. Okay. The derivative of cosine, and remember, because that thing on the right is not in terms of x, it's y, I'm going to have a chain rule here. The derivative of cosine of something is negative sine of that something. We leave the inside alone, and then times the derivative of what's inside. Well, the derivative of what's inside, that's me taking the derivative of something that's not x, so this will be 2 dy dx. Okay? Now, we wanted an expression for dy dx, so now I want to get all the dy dx things over to one side and the non-dy dx things over to this side. Right? Oops, that shouldn't have gone over that far. Okay? So I'm going to go ahead and leave the e to the x sine y on, e to the x plus sine y. E to the x plus sine y on the left. On the right, I'm going to have negative x cosine y dy dx minus, I want to bring that 2 to the front, I think it'll look better, minus 2 sine 2y dy dx. Now that I've got this all over here, I can factor out that dy dx. When I factor it out, I'm left with just the negative x cosine y minus 2 sine 2y. And this is all equal to this left-hand side that's just kind of waiting. Last thing I need to do is divide all of this stuff over so that I can get my dy dx alone. Okay? This is going to give me e to the x plus sine y all over negative x cosine y minus 2 sine 2y. For problems like this, you usually don't worry too much about simplifying. It's kind of going to be a mess, and so you just leave it the way that it is. Okay? This is implicit differentiation. I want to get to one more example of this sort of applied in a context. So let's get to that, and then we'll be done with the lesson for the day. So here's my last kind of like application, right? I'm going to ask us here to find the coordinates of stationary points of this curve. Okay. Now remember, how do we find stationary points? We always find stationary points where the derivative, where dy dx, is 0. So clearly I'm going to be doing the derivative with respect to x. So let's take the derivative of this with respect to x. Okay. Again, I'd recommend you guys pause the video and try this one out. Like, give yourself a chance to see if you're getting the hang of how to do this implicit differentiation. The derivative of y cubed, that's not in terms of x. So this will be 3y squared, chain rule, dy dx. Okay. Now I need to do this thing that's going to take the product rule. Okay. I'm going to do the derivative of the first thing and then leave the second thing alone. Derivative of 3x, that is in terms of x, so it's just 3 times y squared, plus, this time I leave the first thing alone and I have to do the derivative of the y squared. That's not x, so I need a chain rule. This will be 2y dy dx. Right? Finally, we get to this, well, not finally, but last thing on the left-hand side, we get to this minus x cubed. That's in terms of x, so this is just a quick minus 3x squared. On the right side, it's important. Remember to take the derivative of the right also. It happens all the time when people write like 27 over here. You still got to take the derivative over there. Okay. Now, to find the stationary points, I want to know where dy dx equals 0. So my next step should probably be to get dy dx alone. So if you haven't already done this for yourself, take a moment to do the algebra of getting that dy dx alone. I'm going to keep these things on this side, but I'm going to move these ones to the other side. So I'll have 3y squared dy dx plus, let's see here, so this guy here, plus 6xy dy dx equals negative 3y squared plus 3x squared. I wish I'd written those around. Oh well, so actually we can simplify right here. There's a dy dx here. Let's factor out that dy dx. 3y squared plus 6xy equals 3x squared minus 3y squared. And then I just need to take this and divide it over. See, dy dx is 3x squared minus 3y squared all over 3y squared plus 6xy. This is not the answer. Let me make that minus more clear. This isn't the answer, but this is an important step along the way. That's me having found the derivative. Okay? Now, if I want to find stationary points on this curve, what I'm going to need to do is I'm going to need to know when is the derivative equal to 0. Okay, now I need a little more room here, so I'm going to get myself some room. Where would this thing be equal to 0? Well, if this thing was equal to 0, I'd have this, right? The only way this fraction could be equal to 0 is if the top was 0. Another way to think about it is if you multiplied this denominator over, it'll just vanish. You're going to get 0 equals 3x squared minus 3y squared. That means 3y squared equals 3x squared. That means y squared equals x squared. And so when I square root both sides, I'm effectively going to get that y will be plus or minus whatever x is. You might wonder, why don't I put a plus or minus on the left-hand side? Really, the reason is the solutions to this thing are going to be anything where x and y are the same as one another, but they could actually be opposite signs. Like I could have 3 and negative 3, or I could have negative 5 and positive 5, or I could have positive 5 and positive 5. Any of those things are going to be okay. But we're not done. Normally we get to this point and we're like, yay, x was 2. I had this equation here with 2 unknowns in it. How in the world am I ever supposed to deal with an equation that has 2 unknowns? Man, I really wish I had some other equation that had x and y in it. It'd be so amazing if this problem had something else that had an x and a y in it that I could refer to. Hey, would you look at that? The original function. The original function was y cubed plus 3xy squared minus x cubed equals 27. If this is going to work, it's got to work in this original function. Okay, so what I'm going to do is I'm just going to take these things and I'm going to plug them back in up here to find out what x and y values would work. Okay, so as I continue my way through this, so this y cubed will be negative x cubed plus 3x times negative x squared minus x cubed equals 27. Negative x cubed is negative x cubed. I'm sorry, actually, I just realized this should have been plus or minus. right? So this should have been plus or minus. When I do plus or minus x cubed, I'm going to get plus or minus x cubed. When I do plus or minus x squared, it's just going to turn into positive x squared. So this is plus 3x squared, x cubed, minus x cubed equals 27, right? So what I kind of wind up with here is these two things, I'm going to have like 2x cubed plus or minus x cubed equals 27. And what's really happening here is I'm about to get two different solutions for this thing. I could have the plus version of this, which is 3x cubed equals 27, or I'll have the minus version of it, which is x cubed equals 27. In this case, x would be 3, and in this case, x cubed would be 9, which means x is going to be the cube root of 9. Okay, now we're almost done with this thing, right? So this happened over here. This happened over here when y was equal to x. That's what this plus means, right? That was when y equaled positive x. So that means that y is also the cube root of 9, and that means that there's a stationary point at the cube root of 9, comma the cube root of 9. Yay, we found one of them. Okay. This situation over here, this situation happened when y was negative x. That's what this negative means. It means that y was equal to negative x over here, as opposed to y being equal to positive x. Okay, so in that case over here, my y value is going to need to be negative 3, so this stationary point will be 3 comma negative 3. These are the two stationary points that we have for this function. I know that this is a complicated problem. This is a hard one to end on, but I did want to point out that our knowledge and understanding of what we can do with a derivative hasn't changed. We can still use it to do the same things. And we're going to practice this a bit longer, but that's the end of the lesson for today. If you have any questions, please, please, please ask them. Either ask me in class or send me an email or put a note or put a question on your notes when you submit it so I can get back to you. I wish you the best of luck as you work through these exercises.